This is my sixth and last video for Unit 7 on rotation, and this is on angular momentum. So first we'll think about the angular momentum of a point mass, then that of a rotating object. Then we'll talk about the law of conservation of momentum in a system where the rotational inertia changes, and then in collisions. So linear momentum we defined as how hard it is to stop something, and really this is still true for angular momentum, but we have the context of something that's rolling, so how hard it is to stop the rotation, or how hard it is to stop something when it's moving along a circle. So let's just start with recalling linear momentum and what we remember about linear momentum. And Newton actually first wrote his second law, which is the best equation ever, F equals ma, in terms of momentum. So he did it with calculus, so he said that the force is equal to the derivative with respect to time of the product of the mass times the velocity. So this really is the same equation because we know that if the mass stays constant, the change in velocity with respect to time is the acceleration. So a little historical context there. So if we rewrite Newton's second law in terms of velocity or change in velocity, we can see that the net force that would act on a system for a period of time would cause that mass, a single mass, to change its velocity. And so we defined the mass times the change in velocity as the change in momentum, and that's often called the impulse, and that equals the force times the period of time that it acts. So for angular momentum of a point mass, we can think of a mass hanging on a string, and it has a force acting on it, and it is some distance from the pivot of the system. So either there's a string attached to the mass, or if we're thinking about a gravitational system, there's a distance between that planet and the center of mass of the orbit between that planet and another planet. So if we take our impulse equals force times time equation, but then we think just there's a torque acting, so we have a force applied some distance from the pivot point for some period of time, that's going to cause a change in momentum with respect to that pivot point. So all I did between this equation and this equation was I multiplied both sides by r. So that's adding the angular part. So we can define this as the angular momentum of a point mass. And we give angular momentum the symbol capital L. So capital L, the angular momentum for a point mass, is equal to the linear momentum times the radius, or is equal to the mass times the velocity times the radius. And these are vectors, so remember angular momentum is a vector, linear momentum is a vector, these are vectors. And I believe it's a cross product that exists between these vectors, which means that they have to be perpendicular to each other. So in the same way, we can define the, or look at the idea that if a net force causes a change in my linear momentum, a net torque is going to cause a change in my angular momentum with respect to time. So we have our angular momentum for a point mass. That's actually not on the AP Physics 1 reference table, but it's pretty analogous to if we think about our torque equation. Torque is force times the radius, and they have to be perpendicular. So angular momentum is the linear momentum times the radius. And this would be the impulse momentum theorem for angular objects. So angular momentum is L. It has units of kilograms times meters squared per second. So let's look at an example of angular momentum of a point mass. So if I have a ball on a string and it has a mass of 5 kilograms, at the top it's moving at 3 meters per second, and the string has a length of 2 meters. Let's find the angular momentum of this ball at the top. So we would just take its mass times its speed times the radius, and we would get 30 kilograms times meters squared per second. To find the speed at the bottom, we could do conservation of energy to look at it. So we know that at the top it has some gravitational potential and kinetic energy. And then at the bottom, if we call that our y equals 0 point, it just has kinetic energy at the bottom. So the gravitational potential would equal the mass times g, which I'm going to just call 10 for simplicity, times the change in height that it has all the way from the top to the bottom. So that's 4 meters is the change in height. And the kinetic energy it has is 1/2 its mass times its velocity squared. And that equals 1/2 times the mass times the velocity at the bottom squared. So our masses are in every term, so we can divide each side of the equation by 5, and those terms become 1. And so if we solve for the speed at the bottom, we get 9.43 meters per second. So if we find the angular momentum at the bottom, it would be the mass times that speed we just calculated times the radius. So that's 94.3 kilograms times meters squared per second. And that means that a net torque was applied to this system. So let's think about, as it's going down, what forces act on this mass. So we've got the force of gravity that acts from the center of mass, and then we have the tension that acts along the radial line. So what is doing torque? What force is exerting a torque to cause a change in angular momentum here? Is it the tension? Well, tension is acting along the radial line, and we know that torque has a couple equations, but torque is force perpendicular to radius. So those two are parallel, so the tension is not exerting a torque. And so Fg exerts a torque on the ball as it goes from the top to the bottom, and that changes the angular momentum of the ball. So you can think about the ball with respect to some pivot point as having angular momentum. We can also think about it in circular motion. So we've got all these lenses to apply to problems. As we approach the AP exam, we'll look at problems and think about which lens is most appropriate where. Let's think about angular momentum of rotating objects, which I think is a little bit easier. So the angular momentum of a rotating object is equal to its moment of inertia times the angular velocity. And we can kind of derive that from the previous equation we had for angular momentum. But when we look at a rotating object, let's say a record or a rotating disc, what we're going to look at is if we had our other linear momentum or angular momentum equation, which is L equals mvr, we want to take each chunk of mass and consider the angular momentum of each of those chunks. So we're going to add up. We're going to take the sum of all of those mv times r's. And so if we do that and we express v in terms of its angular velocity, because we have something rotating, it would be the sum of the mass times the angular velocity times the radius, which is the linear velocity, again times the radius. So then we get the sum of the mass times r squared, I'm just pulling that out front, times omega. And we know that this is the moment of inertia. That's a little derivation for you. So this is the equation that's in your reference tables, the L equals I omega, and that's going to be an important one when we think about angular momentum of things that are spinning about an axis. So, summary, angular momentum of a point mass is linear momentum times radius. Angular momentum of a rotating object is moment of inertia times angular velocity. And a net torque would cause a change in the angular momentum, just like a net force caused the change in the linear momentum. And if there's no external torque or no torque on the system, then the angular velocity, the angular momentum change is zero. So we know that the change in angular momentum is equal to the torque times time, and if there's no net torque on the system, then our change in angular velocity for our system is zero, and that leads us to conservation of angular momentum. That in a closed system, the total angular momentum stays the same. So if we have this ice skater, it's just one object, so closed system, and there's no external torque, so the change in angular momentum of this ice skater needs to be zero as the ice skater pulls their arms in. So we can consider how their rotational inertia changed. So initially, the rotational inertia with the arms out was very large, and the skater was spinning slowly. And then when the skater pulls their arms in, that decreases the rotational inertia of the system, and that causes the angular velocity to increase because angular momentum needs to be conserved. So the closer the mass is to the rotation axis, the smaller the rotational inertia, and the smaller the rotational inertia, the faster the rotational velocity in order to conserve angular momentum. Another example of conservation of angular momentum is with collisions, and these ones are some of the trickier problems, I think, but they're really similar to our linear momentum. So momentum is always conserved in a collision, and the thing about that might not be conserved is the energy. So in elastic collisions, the kinetic energy is conserved, or the total energy is also conserved, and we have very few of those elastic collisions. We also need to remember when we do collisions with rotating objects, that momentum is a vector, and you should use positive or negative to indicate clockwise or counterclockwise directions. So all collision problems you would approach through the lens of conservation of angular momentum. And if you have like two rotating disks like we had in our homework set, you would approach this problem just by finding the initial angular momentum of the first rotating disk and adding the angular momentum of the second rotating disk, remembering that if the disk is rotating in the opposite direction, then we do need to call it negative. And then in the end, whether they stick together or not, you can still express the final angular momentum as the initial moment of inertia, or the first one's moment of inertia times the final angular velocity of that one, plus the second one's moment of inertia times the final angular velocity of that one. So if they stick, this really results in those rotational inertias adding together, and each of them moving together with some final angular velocity. But if they don't stick, then you can keep them separate. So here's an example AP question that kind of combines linear momentum and angular momentum of different things. So we have these three cases where we have a rod, and we're going to ignore all friction between the pivot, between the floor. This is a top-down view. And the mass has some linear velocity Vp, so I think this is a puck, that's why it's called P, and rebounds off of the rod. And then in case 1, in case 2, the mass just stops, and then in case 3, the mass sticks to the rod. And it asks us to rank the magnitude of the angular displacements through which the rod rotated in 2 seconds, using 1 for the greatest, 2, 3, so on. So which one is going to result in the greatest change in momentum? So one of the big ideas here is that the change in angular momentum of the puck is going to equal the change in angular momentum of the rod, because the change in the angular momentum for the system is going to be 0. So each of the objects needs to experience the same change in angular momentum, just like each of the objects experience the same force in the interaction. So that's Newton's third law. So the puck is going to undergo a greater change in its momentum, either linear or angular, because it has undergone a greater change in velocity. So if this was like 2 and this was -1, then the change in velocity in this case would be 3. Whereas if this was 2 and this is 0, the change in velocity with this case would be -2. And then in this case, the whole system is going to slow down. So if it was 2 and then maybe it's rotating and the linear velocity there is 1, the change in velocity would just be -1. So the puck is going to undergo a greater change in velocity in the first case, and so the rod, and therefore a greater change in angular momentum. So the rod is going to experience the same greater change in angular momentum as the puck, and because they have a greater change in angular momentum, it's going to have a greater rotational velocity. So a greater change in angular momentum means a greater change in the rotational velocity, and a greater rotational velocity means a greater angular displacement for the same time. So the rank here is 1, 2, 3. So that was comprehensive in my longest video, but I hope that was helpful, and feel free to shoot me any questions.